Welcome to Investigation 3.4, Quadratic Functions and Patterns of Change. So we're going to be looking very specifically as to why a quadratic function is a quadratic function and how you can find the change that occurs in a quadratic function through tables. We know that with linear functions, when we have a linear function like y is equal to 2x plus 1, we can essentially create a table of values for x and y and look at how things change with 0, 1, 2, and see that at 0 it'll be 1, and then it'll increase by 2 each time. So the plus 2 that's how we see it in our slope. As well with exponential functions, we're used to seeing that multiplication of something or that division of something if we're seeing a decay. Regardless, with quadratic functions, we're going to be seeing a very specific pattern of change, but it won't necessarily be really obvious right away, which is something you've probably already noticed so far. So our focus of this will be comparing the pattern of change for a quadratic function and comparing it to patterns of change for linear and exponential functions, two things that you're very familiar with. So let's do just that. Our very first part of this investigation has us making a table of values for each of the quadratic functions or quadratic equations below. Include the integer values from x being -5 to +5 and show the first and second differences. So doing that, we are going to be seeing a very interesting pattern. And first of all, we need to find out what first and second differences are. So I'll show you exactly what that is. Very first thing, let's actually turn our second equation into its FOILed expanded form. So we're going to say x times x, x squared. We have then 1 times x, 1x. We have 3x. And lastly, we have plus 3. So we have x squared plus 4x plus 3 is our equation that we're going to be working with. So let's zoom in on this a little bit and see exactly what we need to do. First of all, they tell us to make a table from -5 to +5. After that, we actually need to do a little bit of math work. We need to put -5 into our equation. So if we said -5 squared plus 4 times -5 plus 3, we need to figure out what that is. -5 squared would get me 25. 4 times a -5 would get me I'd be subtracting 20, and then I'm going to add 3. So 25 minus 20 is a +5, and then I'm going to add 3, so I get 8. So at -5, I'm at 8. We need to fill in the rest of this table, so I am going to do just that. So now we have the table completed, and now we have to see what a first and a second difference is. And I'm going to show you how to do that with two different colors. Our first difference is going to compare how everything changes initially. So our first difference is sort of surface changes, and we're used to looking at this. We've looked at this through linear equations and exponential equations, and sometimes it's a multiplication pattern and sometimes it's an addition pattern. This time, what we have been doing is looking for addition patterns, and so we can kind of play around with that. If I look from 8 to 3, it looks like I'm subtracting 5. So it looks actually, in this case, that I am going to be subtracting initially. I'm going to then subtract 3, then it looks like we're subtracting 1, then 1 to 0, I'm adding 1. 0 to 3, we're adding 3, we're adding 5 next, we're going to add 7, 9, 11, and then finish off with 13. So this is what's called our first difference. So we're looking at how everything changes initially, right away between each of the numbers. Now we also, with quadratic equations, we can look at what's called a second difference. So we can look now at the differences between the numbers and the patterns that we're seeing here. And with quadratic formulas and quadratic equations, you'll notice that the second difference will show us the consistency we're looking for. If I look to get from -5 to a -3, I need to be adding 2. If I go from -3 to -1, I again need to add 2. From -1 to +1, we're adding 2. And you'll notice this is our consistent pattern that we've been looking for. We're adding 2 each time all the way through. So that is our second difference. And that difference, when we're looking at tables, proves that we have a quadratic formula, or a quadratic equation, and that's what we are looking for. Let's do the same thing with this second equation that we have here. I'm going to show you the table, I'm going to show you the first difference and the second difference, and it'll just be a little bit of math magic. So bear with me, and in a second it will show up on your screen. Okay, so this table is kind of a little bit more funky. Looking at this table, our initial gut instinct is saying this isn't a quadratic function. I don't see any point to which there is a perfect mirror image. And in all reality, our perfect mirror image is happening on a fractional piece. So our perfect mirror image is going to be a little funky. So now I'm going to show you the first and second differences, just like I did before. So a little math magic will appear on your screen in just a moment. So now you can see the first and the second differences. Looking at the first difference, if we're looking at that -42 to -34 to -26, -18, -10, -2, 6, 14, 22, 30, we're not necessarily seeing that consistent pattern, mainly because those numbers are so far off from each other. If you look at our second differences, though, we're seeing a +8, +8, +8, +8. And because of that, we can say this means it's quadratic. And then another indicator, if you've been listening to what I've been mentioning every once in a while, our highest exponent value that we can see within a quadratic function typically can only be a 2. It can never be higher. If it's any lower, we have either a constant value or we have a linear equation. But we're always looking for a value that's a 2 as an exponent. So those two things with an equation, looking for that x squared value and nothing higher than that. And then in a table, looking for that change in our second differences, this sort of thing, is what we are looking for. Those two indicators will help us find a quadratic equation. So let's look now and answer what is the pattern of change that seems to occur for quadratic equations. And we can say the second difference is a constant. So it's constantly increasing by something or constantly decreasing by something. Our next part of this particular investigation is looking at various tables for other quadratic or non-quadratic equations. So make a table of xy values for each of the equations below. Show the first and second differences. So looking at our first equation, we can recognize that immediately. That is that y equals mx plus b format. It is linear. The next one we should know, or actually this isn't our next one, it's kind of our third one. It is exponential. Our one down below, technically our second one, is also a linear format. And our very last one is our indicator of quadratic because we can see that x squared value. But let's look exactly at what happens with those first and second differences and see what occurs. So let's zoom in and fill out our first table altogether, and then after that I will fill in the other ones for us. So if x were equal to 0 for this first equation, if x were equal to 0, y is going to equal 3. If x was 1, y would equal 4. If x was 2, y would equal 5, and so on. And we're increasing just by 1 each time. Our first difference, I'm going to do in purple, and we can see there's a +1, +1, +1 each time. And our second difference, I'm now going to put in red, and our second difference, the difference between 1 and 1, is absolutely nothing. It's 0. 0, 0, 0. Kind of interesting. So let's fill out the other couple of tables, and we will see what exactly happens for each scenario. So I'm going to move on, and eventually you'll see a whole different screen, and it'll have a little bit of math magic occur. So now we can see the completed tables for all of them. If we look at our first initial table, we can see our first difference for this linear equation was a consistent +1. Our second difference, though, ended up with straight zeros. So we already had the consistent pattern in our first difference, which is kind of interesting. For our second version, we had, again, another linear pattern. So we saw a consistent +3 each time. That shows us that slope that we're recognizing. And then our second difference, again, we had that 0 second difference. So the linear pattern is always going to show us a 0 in our second differences because our consistency is something that we can see within our first difference. If we look at our exponential function, look at this baby, letter C. Our first difference, I'm going to zoom in on this one because it's kind of interesting. Our first difference is showing us absolutely no consistency whatsoever. There's +4, then +12, we have +2, +6, +18, +54, +62. And then if we were looking at the second difference, again, there's absolutely no consistency. We have a +4, +12, +36, +108. So it's a possibility that exponential functions aren't ever going to show us a difference that's something that we can look at, mainly because it's not an additive difference. It's a multiplicative one. We are multiplying each time by 3, and we can see that within our first multiplicative change. So that's kind of interesting about how we see the exponential functions. Let's look down at our quadratic one, that one that we know is quadratic. And we can see that there is +3, +5, +15, 21, and 27 for our first differences. So we're seeing very little consistency. But when we look at those second differences, as long as we are being very careful with our math, which is incredibly important for this, we can see that there is a +6, +6, +6 constant second difference. And so that's kind of an interesting pattern and it's pretty cool. So our next part is how can we use the pattern of change in tables to identify the type of function? And what we can look at is for linear functions, we can sort of summarize that linear functions will always show a constant first difference. We'll see that change right away just by that additive or subtractive difference each time. But for an exponential function, we will see absolutely no pattern whatsoever. We will see very little pattern. Why? Because it is, it is a multiple problem. You're multiplying each time. It's a multiplicative difference. So there's a change based on multiplication. The very last one for quadratic functions, we will see a constant change in the second difference. So the second time we go through that sort of what is happening here, the second time we go through that, we will start to see that change become consistent. So that's kind of cool. I'd like you to work through this investigation, have fun with it. It's pretty cool. Enjoy. Find those differences. If you have any questions after you're finished, please ask. Thank you so much for listening and watching, and I will see you later.